An experiment was carried out to determine the partition coefficient of iodine between water and organic solvent. So iodine, it will be a little bit highly dissolved in organic solvent, but in water, normally it does not show much of an solubility. But still there will be a very small solubility. That is why we usually store I2 in Ki solution than just water, because I3 minus is stable. Okay. So 20 cubic centimeter of B, which is our organic solvent, containing n moles of I2 is mixed with 20 cubic centimeter of A and allowed to reach equilibrium. So basically, we will have 20 cubic centimeter of B and 20 cubic centimeter of A, right? So A and B is there. But in B, you have n moles of I2. So when you shake it with the A, so there will be this equilibrium between the I2 molecules, and at equilibrium, their concentration is going to be constant, right? And they say the concentration of I2 in phase A is determined by titrating. So this is 20 cubic centimeter. So you get 5 cubic centimeter from A, and you know what is going to do, right? So you normally titrate with sodium thiosulfate, Na2S2O3. So I think this reaction is now like father of the reactions that you have in this chemistry questions. So 5 cubic centimeter sample is drawn from phase A, and it was titrated with sodium thiosulfate, and the concentration is given 0.005 m, and the volume is 22. So it consumed 22 cubic centimeter. And the concentration of I2 in phase B was determined to be 0.04. So this is already found. It might be using the same process. So this was found as 0.4 m. Write the balanced chemical equation for the reaction of Na2S2O3 with I2. So this is very, very common. We have done this, I think, many times. So with I2, so it gives you, put the physical state, so aqueous. So this will give our NaI plus the tetrathionate, Na2S4 and O6. Okay, so you can put here 2 here and 2 here to balance. Yeah. So calculate the concentration of I2 in phase A. So first what you can do is find the concentration of, find the number of moles of sodium thiosulfate here. So it will be 0.005 times 22 times 10 to the power minus 3 moles. And using the stoichiometry, you can find the amount of iodine present in 5 cubic centimeter. Don't forget, right? So it will be 0.005 times 22 into 10 to the power minus 3 here, divided by 2, because the stoichiometry is 2:1. So that will be in 5 cubic centimeter. Then you have to again multiply that amount by 4, because you have to find the total I2 in 20 cubic centimeter. So here there's only 5 cubic centimeter. So you can just multiply it by 4 to get the total number of moles, and divide it by 20 to get the concentration. Because since they ask only the concentration, just you can find the moles here in 5 cubic centimeter. So you find the moles divided by 5 and you get the concentration, because concentration here and concentration is here is same. The only difference is the number of moles. So either you can find the concentration directly here, or you multiply by 4 to get the total amount, then you divide it by the total volume. So in the same case, same thing. So you can find it. And calculate the value of the partition coefficient Kd, where Kd is I2 in B, which is our organic phase, over I2 in A. So you know the concentration of B already, so it is 0.04. So this is 0.04 m. And when you find the concentration of I2 in A, you will find it will be 0.011, which is going to give you a KD value of around 3.64. Okay, so which is a little bit good because it shows that I2 is more soluble in phase B, which is our organic phase, than in water. Okay, so that is done. And the next one is calculate the total number of I2 moles into phases A and B. So this is what I told you. So when you know the concentration, it will be very easy because you know the concentration of I2 in B and you know the concentration of I2 in A. So just you have to multiply it by the volume of these two phases. So the total I2 will be like I2 in phase B, so it will be like 0.04 m times the total volume, which is 20 cubic centimeter into 10 to the power minus 3 moles. So this will be 20 plus the concentration that is in phase A is 0.011 times again 20 times 10 to the power minus 3 moles. So this will be the total amount. So you can add those two and get the total amount. Okay, so that is a very simple idea. Yeah, so this is done. So you see, this is a normal typical homogeneous phase equilibrium question, right? Finding the partition coefficient for an equilibrium of I2 in sodium thiosulfate after the titration. Then we move into question number B. The above experiment was repeated until the same condition, under the same condition, that is at the same temperature. So very good. So your KD, which you found as the I2 concentration in the organic solvent, which is I guess B here, over A is not going to change. It will be same as 3.64 because the temperature is same. And using the same amount of I2 and the same volumes, but with the addition of I minus ions to phase A. So this is why I told you in the beginning, normally when I2 is not soluble more in water, which is our phase A here, you add a little bit of I minus so that its solubility is now a little bit of high. So we use same amount of I2, which gives you the idea it is the same amount of I2 here, the total amount. So when you find the total amount for the last question in question number 4, you will see the total amount is 1.02 into 10 to the power minus 3 moles. So you can keep that in mind. 1.02 into 10 to the power minus 3 moles for an example. So when you find the total amount here, so we use the same amount here, same volume, and we add a little bit of I minus. The system was again shaken thoroughly and allowed to reach equilibrium. The volume of 0.005, again same sodium thiosulfate to titrate I2 in this sample, 5 cubic centimeter sample of phase A was 41. So you see here there is a little bit of difference now. So same B and A, same volume, 20 cubic centimeter. So here also 20 cubic centimeter. But in phase A, we have added a little bit of I minus here. So which is will be in reacting with I2, which is in equilibrium here with the organic phase. And there will be another equilibrium, small equilibrium, like giving I3 minus as well. So don't forget about that. And they take in the same way 5 cubic centimeter, and they see here sodium thiosulfate versus 41 cubic centimeter. So it is found. It is from me. And again, they found the I2 concentration in B here is 0.030. And they say the first question, calculate the amount of I2 mole expected in 5 cubic centimeter of phase A based on the partition coefficient. Sorry, for the distribution of I2 between phase A and B. So we have this partition coefficient, right? And we have this concentration of I2 in B already. So it is like just a simple math, because we know this one already 0.030, and you just need to find I2 concentration in phase A using this small calculation, right? Because this becomes very straightforward. So that is very simple stuff here. So you find the concentration of I2. So, but we have to find the number of moles. So after finding the concentration, just multiply it by 5 into 10 to the power minus 3 decimeters. So you will get the amount of I2 in 5 cubic centimeter of phase A, right? So that is very easy. Then calculate the amount of moles of I2 reacted with sodium thiosulfate in the above reaction. So it is again very similar, right? So you know the concentration of sodium thiosulfate and you know the endpoint volume. So it will be 41. So 0.005 into 41 into 10 to the power minus 3, which will be the sodium thiosulfate amount. Then half of that will be the I2. So where is it? So you find the amount of I2. So basically, when you find the amount of I2, you will see it will be around 1.03 into 10 to the power minus 4. Okay. So that is the way that you can calculate the sodium thiosulfate amount. So that is also very simple. So this is, you can go with the KD, find the concentration, multiply by 5 cubic centimeters, so you find the total amount. And calculate the total moles of I2 reacted with sodium thiosulfate, so you can find it. Considering the different iodine species present in phase A, explain why the answer obtained in part B1 and B2 above are different. So you can explain that, right? You see here, there is a different story happening here. That is very important to understand. Okay. So why do you think that, so if I get the real correct options here, so when you just use the partition coefficient and you calculate the amount of I2 moles here in phase A, so you will be end up in like getting 4.1 into 10 to the power minus 5. So here it is 4.1 roughly 10 to the power minus 5. But when you find those things using the thiosulfate, the actual titration, you will get something around 1.025 into 10 to the power minus 3, right? So you see here, there is a big difference. This amount is a little bit of higher than this one. And they are asking why? That is our question. So the simplest explanation is here. You see here, when you have I2 in phase A, it combines with I minus and it forms I3 minus, and this is a stable complexation reaction. Okay. So when you take 5 cubic centimeter from this, and when you do the titration with sodium thiosulfate, this I2 is going to react. So this concentration drops out when this is reacting with sodium thiosulfate. Then this equilibrium is shifted more towards this direction, and more of I3 minus is converted to I2. So that it's like all the I2 that is going to be in this phase A is going to react. It is not only the I2 that is in equilibrium where we find through KD. because through KD, we find only the I2 that is in equilibrium with the I2 in phase B. But with the sodium thiosulfate titration, we find that I2 that is in equilibrium with this I2 in phase B, and also we find the I2 that is already present in I3 minus, because when I2 is reacting here, this equilibrium is shifted toward the right hand side, and all I3 minus will be again converted to I2, and we find this total I2 from this titration, and that is why we get a higher value here. Okay, so you can explain very simply this I2 in phase A combines with I minus and form I3 minus, but we get a higher value for here in the sodium thiosulfate reaction, because this I2 when reacting with sodium thiosulfate, this all I3 minus is again going to form I2, and this I2 also going to react with sodium thiosulfate. So that is the clear explanation for that particular question. Okay, so that is very important to understand. Please try to understand this. Okay, very important here. And the last part of this question, so it is part C. Liquids X and Y form an ideal solution obeying Raoult's law, so which is good. So we will have liquids X and Y forming the ideal solution. So there is vapor phase introduced to liquids, and liquid level, liquid phase, piston to adjust the liquid. So who cares about this picture? So only some additional picture is given to just to scare you, but don't worry about that. So initially only liquid X was introduced to an evacuator digit container as shown in the figure. So only X is there, right? Maintaining the liquid level at L. So there is this liquid level at L. Okay, the system was allowed to reach equilibrium at 400 Kelvin. So we have only X here initially, and the temperature is 400, it is given. And the pressure of the container was measured to be 3 into 10 to the power 4. The volume of the vapor phase when the liquid level is at L was given. Then liquid Y was introduced into the container, mixed with liquid X, and the system was allowed to reach equilibrium at 400 Kelvin again. And the liquid level was maintained again at L. And the molar ratio in the liquid phase was found to be 1:3. And the pressure of the container was measured to be 5 into 10 to the power 4 Pascal. So if I just sketch the two situation, right? So this was 400 initially, and for an example, if I just sketch the situation, both situation here, so you have X liquid, and for an example this X, and you keep initially X, then you mix it anyway. So this is 400 pressure of the container, so you measure the pressure, it is 3 into 10 to the power 4. And the volume of the vapor phase when the liquid level is at L, so this volume is given 4.157 V, and this is P, and this is X. So then you introduce Y here, so then you have X and Y both here. There will be some amount of Y dash here, equilibrium, just to show different moles. And sorry, so at 400 Kelvin again it was allowed to equilibrate, and again same level is maintained, so we don't care about that. And the molar ratio here, X is to Y, the liquid phase is given. So it is 1:3. And the pressure is measured here again. So this total pressure now will be from X and Y. So this is 5 into 10 to the power 4 Pascal, right? So there are questions. So what is the saturated vapor pressure of X at 400 Kelvin? So what do you think? So you see here, initially there was only X, right? So X will be recuperated in, for an example, with its liquid state. So in the liquid, there is only X. So there will be no other component. So if you want to calculate the mole fraction time, the Raoult's law. So if you just think about your Raoult's law for an example, like you try to find Px is equal to P naught X times X. So Xx will be 1 because there is only X here. So automatically the saturated vapor pressure is equal to Px, which is this one, right? So this is very simple. Because since there is only X, its pressure is going to be equal to the saturated vapor pressure. Okay. And the second one, calculate the mole fractions of X and Y in the liquid phase at equilibrium. So they have given the mole ratio. So X will be 1/4 here because 1:3 means 1/4. And XY here will be 3/4 because 3:1. Okay, so these are very, very simple cases, right? Calculate the partial pressure of X at equilibrium after the addition of Y. So from the first case, you find the saturated vapor pressure of X. So here you just have to add the Raoult's law here. So Px will be equal to P naught X XA. So P naught X you already found here. That is 3 into 10 to the power 4 from the first case. And XA is found here. That is XA in the liquid phase. That is what it is in the Raoult's law also. So it will be 1/4. So this will be like 0.75 into 10 to the power 4. So it will be like 7.5 kilopascal, I would say, if I am not mistaken. Okay. Then say calculate the partial pressure of Y at equilibrium. So here they have given you the total pressure, which is like 5 into 10 to the power 4 means 50 into 10 to the power 3 Pascal, which is 50 kilopascal. So you know now 50 kilopascal, which is the total vapor pressure, should be equal to Py plus Px, which is 7.5 kilopascal. So basically Py is around 42.5 kilopascal. Okay, so this gives you the idea. Py is more of like high vaporizer. That means Y is more volatile than X, right? Because you see here Y has a higher vapor pressure. At this molar ratio, Y has a higher vapor pressure than X, right? So this is done. This is done. So this is done. So calculate the saturated vapor pressure for Y. So it is again the reverse now, because you know Py is equal to P naught Y XY in the liquid phase. So Py you know now 42.5 kilopascal. P naught Y you don't know, but you know XY, which is 3/4. So this will be 3/4. And you don't know P naught Y, but this will be equal to Py, which is 42.5 kilopascal. So you can automatically find P naught Y here. Okay, so these are very simple things. Then calculate the amounts in moles X and Y in the vapor phase. So now this becomes very straightforward, because now for an example here, now here we apply the Raoult's law for the solution, right? And we know all the vapor pressure of X and vapor pressure of Y, and even we know the temperature, right? And also we maintain at the same level L, so which means we know the volume as well here. So the volume here also will be the same here, and we know the total pressure here in the vapor phase. So we know P, we know V, which is 4.157, and we know T. So you can apply PV is equal to nRT to find the total number of moles here in the vapor phase. That is one thing. And if you know the total number of moles and you know the partial pressure of Px and Py here using the Raoult's law thing, so you just have to find the mole fraction and get the number of moles. So it will be very, very a simple calculation, right? So you can directly find the X and Y by using their partial pressure. Oh, okay. So you can do that in both ways. Or either you find the total number of moles first using the partial pressure, then find the number of moles. Or since you have the partial pressures of X and Y in the vapor phase, you just apply VPV is equal to nRT for X separately and Y separately and find the number of moles. Okay. So those are very straightforward. When a mixture of liquids X and Y is subjected to fractional distillation, so we use fractional distillation to separate the compounds. So more volatile compounds will be separated more, and we can get pure form of them. State which compound will distill out first from the fractional distillation column. Give reasons for your answer. So our answer came from the beginning, because you see here when you check for the saturated vapor pressure, just try to get the saturated vapor pressures. You will see here for the Px, so it will be very, very small one, but for P0Y, it will be very, very high. So P0Y is higher than P0X. So which gives you the idea Y is more volatile. So Y is more volatile means it will be more coming out from the fractional distillation column, so you can separate very easily, right? So they are asking which compound would distill out first. So Y is going to distill out first. What is the reason for that? The volatility of Y is higher than volatility of X. That would be the simple answer. Or you can explain P0Y is greater than P0X, therefore its volatility is high, and therefore it will come out first from the distillation column. Okay, so this is also done.